This video is going to talk about the idea of universal logic gates and provide an example of how they can be used to implement an example logic function. So a universal logic gate is a gate or possibly a set of gates that can implement any desired logic function. The two most common universal logic gates that are used are NAND gates and NOR gates. And in this video today, we're going to focus on using NOR gates as a universal logic gate. So a NOR gate itself implements a not or operation, and so for a two inputs NOR operation, the gate would look something like this. And so the first thing you might think about is, well, how can we use this NOR operation to implement other types of logic functions? So another common logic function is a NOT operation. And so the question would be, how can we use a NOR gate to implement NOT? And if we think about it, a NOR or NOT OR, if both inputs to the NOR gate are 0, then an OR gate would give us 0 and a NOR gate would give us 1. And if both inputs are 1, we're going to get a 0 out. So to create a NOT gate with a NOR gate, we simply have to connect the two inputs together and we can have a NOT functionality. We could then also be interested in how we could perform an OR operation. And so if we already have a NOT OR operation, if we NOT the output of a NOR operation, then we would have an OR operation. So if we take our NOR gate and then NOT its output by using the NOR or the NOT operator that we just created, we can create an OR gate by composing two NOR gates together. And then maybe not the last, but the last one we're going to look at operation would be an AND operation. And there are a couple of different ways we could come about developing a set of logic gates to perform an AND operation. To help us out here, we're going to look at De Morgan's law and look at the fact that if we have A or B NOTed, which is essentially our NOR operation, we could apply De Morgan's law and say that this is going to be equivalent to NOT A and NOT B. At this point, we're kind of halfway there. We have an AND operation, but we have it with the inverted version of both of the inputs. So we really want to invert those inputs again. So we essentially want to be able to add or invert these inputs again, so we end up with A ANDed with B. And so if I was to draw this out, one way to think about this would be that we've got an AND gate where both of the inputs are inverted, and we'd really like to invert both of the inputs to that, so we end up with A and B going into our AND gate, and we get A ANDed with B. And so since we're only using NOR gates here, this is really just another version of a NOR gate. So this is a NOR gate, and then we've already shown how we can draw inverters or create inverters with NOR gates. So we can add NOR gates to this, and now we have how we can implement an AND gate making use of only NOR gates. And so to look at a specific example of how we could implement a logic function using only NOR gates, we're going to look at the function NOT A ANDed with B or C. And there are a few different ways we could approach this. One would be to basically take these gates that we developed on the left and just put them into each of the places we need here. So the outermost function that we need is an AND operation where we're ANDing NOT A with B or C. So for the AND operation, we said that we had this section that we just created where we use 3 NOR gates. And then we need to, in the top one, feed in NOT A, and into the bottom one, we need to feed in B or C. And so for NOT A, we need a NOT gate. So we can feed in A into this, and then for the bottom section, for the bottom input for B or C, we need an OR gate, which we said we could form with a combination of essentially a NOT gate combined with a NOR gate, and into this we could feed in B or C. And we could stop here, but if we looked at it, we'd see that this isn't necessarily the most efficient use of gates here. So if we look at this section and this section, we see that we essentially have two NOT gates or two sets of NOT gates chained together. And so in both of these cases, we really got a NOT gate followed by another NOT gate, and this is equivalent to a wire from a logical perspective. And so we could redraw this as simply A going into our NOR gate, and then one other NOR gate that is taking in B and C. And so here we can see how we can implement this logic equation making use of just two NOR gates. Another way to approach this would be to see if we can rework this equation in a way that makes it, or where it's mostly represented as a set of NOR functions. And so if we take our not A and B or C, and if we negate this twice, so we haven't changed it because negating something twice is equivalent to the same thing. And if we apply De Morgan's law once to this, we can see that we'd have not A ORed with not B or C, and this entire area, or this entire operation, negated. And so within this, double negation of A is just A, and then we have B or C negated and the whole quantity negated. And if we look at this, we basically got two elements that are NOR operations. So we've got this B or C inverted, and so essentially we have a NOR operation here where we've got B and C coming in, and then additionally this entire case is a OR operation that is negated, and so we have the B or C negated coming in as or along with our A input. And with this approach we get the same answer that we had before. And so this shows two techniques for using universal logic gates to implement an arbitrary logic function.